Hi there. Often vintage devices land on my bench, for example this one. On these I'm always wondering if I should just plug them into mains and turn them on or not. If there is some serious fault, a lot of hard to repair damage can occur with magic smoke release before the mains fuse blows, a circuit breaker pops, or I manage to turn it off manually. On low volts DC we are all used to power supplies that allow us to set a limit, so if the worst happens, the current is limited and therefore any serious damage in the connected circuit can usually be avoided. This video is about building something similar, although much simpler for mains AC. The idea is very old and uses an incandescent light bulb as a resistor to limit mains current into a device under test. It has to be an incandescent light bulb, such as this 60 watts 240 volt version here. Its cold resistance is about 68 ohm as shown by the meter on the right. But when hot, that is producing light, this bulb draws only 0.261 amps at 242 volts, from which you can calculate that the resistance has increased from 68 ohm to 927 ohm. Incandescent light bulbs are PTCs, that is resistors with positive temperature coefficient. The hotter they get, the more resistance they show, which limits the current and therefore the temperature. This effect makes them ideal as current limiting resistors. Different incandescent bulbs have different resistances. This 100 watt 240 volt bulb has only about 44 ohms cold. But hot, it draws 0.466 amps at 242 volts. In other words, it acts as a 519 ohms resistor. In general, the more watts a bulb has, the lower the cold and hot resistance. Also, bulbs for a country with lower mains voltage will have a lower resistance for the same wattage compared to these 240 volt bulbs. But don't worry, you can use any bulb suitable for your country, just make sure it's truly an old-fashioned incandescent bulb and not using LEDs. Some of these LEDs now look a lot like incandescent, but no, you can't use them. The circuit is simplicity itself. The light bulb is simply wired in series with the device under test, or DUT. When the light bulb is cold, its resistance is low and almost the entire mains voltage is available to the DUT. If it behaves well, it draws only a little power, which might not even be enough for the light bulb to emit any light. If it needs a little more, it might make the light bulb glow dimly. But if there's a serious problem in the DUT or even a complete short circuit, it will try to draw a lot more power from the mains. This current will cause the light bulb to glow brighter and brighter and increasing the resistance at the same time, limiting the current to both bulb and DUT. This method is not as comfortable or versatile as an electronic current limiter you saw earlier, but it does the job of preventing serious damage. And you can adjust the current limit somewhat by using different light bulbs. The higher the watt number, the more current can flow. I deliberately did not use voltages in this diagram because this works for either 240 volts or 115 volts, just use incandescent light bulbs available in your country. And speaking of availability, incandescent bulbs will eventually burn out, but in this application they will basically last forever. However, incandescent bulbs are increasingly difficult to buy, and so you may want to stockpile a few for use as PTC resistors. I have used this method before, but I'm getting tired of jury-rigging a light bulb every time I have a new DUT, and flying connections running mains voltage are not a safe practice. Therefore, I decided to build a little box that houses this circuit here. I tried to make it as cheaply as possible with what's available in the UK. If you build your own, by all means use whatever is available in your country. But please, building and using involves mains voltage, which is dangerous. So you need to be comfortable with this, and if you follow along, you do so at your own risk. With that out of the way, you notice a few additions to the principle shown before. One side ends in a mains plug and the other in a mains socket, which makes it easier to use. I should also mention that in the UK mains plugs have built-in fuses, which I have not shown here. I put a 3 amp fuse in, since this is not intended for high-powered DUTs like fan heaters. If your country has no fuse plugs, you may want to consider adding a fuse inside the box, that is, using an inline fuse holder. There's a bypass switch which simply short circuits the bulb. This allows you to pass unlimited current to the DUT once you are happy that it can handle it. And there is an on-off switch. I labeled it optional because in the UK most sockets have an integrated switch, so I got it without extra cost or wiring, but having an on-off switch is just convenient, not essential. With all this said, the usage is very simple. You may have seen similar devices used in other videos. For example, Mr. Carlson's lab uses such a device with 2 bulbs wired in parallel for higher watt rating. I don't think I need much more than 100 watts, so 1 bulb will do, at least for me now. Start with the bypass open and connect the DUT and turn it on. If the DUT has a fault, the bulb will glow brightly. If so, turn the DUT off, disconnect from mains and investigate. It's not always the case that a bright glow means a problem. That depends a bit on the DUT. For example, it might draw more initially when cold and then draws less, like a valve radio. In this case, you may wait a few seconds to see if the brightness subsides. Or your DUT may be by design draw way more than the wattage of the bulb, in which case you need a bulb with higher watt rating, so check the specs of your DUT. If the bulb glows only dim or not at all, you can close the bypass and give it the full mains power without any limiting other than the fuses that might be in the circuit. Of course, no glow at all could have other reasons as well. If there's absolutely nothing happening in your DUT, there might be an open connection like a blown fuse. Anyway, enough of theory, on to the build. In the UK you can get these standardized patron boxes very cheaply in the electrical section of any DIY store. I used 2 of the plastic variants with 40mm depth. These are normally meant to be mounted on walls, and their standardized size fits switches or socket front plates sold separately. I marked this one for a half circle cutout. And here's the second box with the same marking. I will mount these 2 boxes back to back, so this cutout is really a circle for the lamp socket. The lamp socket I used is a ceramic type for Edison type lamps called E27. It has 2 terminals at the back for electrical connection. I removed it from this plastic holder, which was meant to be mounted as a light fitting in attics or cellars. These type of fittings are called button lights, at least here in the UK. I used a Dremel with a cutting disc to cut out the large rectangular hole in the back of the boxes and a grinding bit to make the half circles. The plastic of the patron box is extremely hard and brittle. Dremel tools work well on it, but produce a lot of very fine dust, so wearing glasses and breathing masks are essential when doing this. I drilled a large hole in one of the boxes for the power cord. The lamp socket fits into the hole and is held when the 2 halves are screwed together. If this is too loose, use a drop of glue to hold it. The socket does not get very warm since normally the bulb is not on or very dimly. I drilled 2 small holes through the back of both units for 3mm screws to clamp the 2 halves together. Wiring this simple circuit is very straightforward. This here is the bypass switch, which is simply a standard light switch on a front plate for patron boxes. And this is the opposite side. You can see the 2 screws holding the boxes together back to back and the strain relief for the incoming cable. A normal UK main socket front plate with integrated switch closes the box. To test if everything works as it should, I connect the multimeter between the hot or live of the plug and the hot or live of the socket. If the on-off switch is off, there should be no connection. When turned on, with the bypass switch on the back in the open position, you should see the cold resistance of the bulb inserted in the socket. And if the bypass switch is closed, the resistance should be nearly 0. Well, in this case it's about 0.9 ohms because of the cable resistance, but mainly because of the fuse in the UK socket. Eventually I may spend some time to make this more pretty, but for now I just put some quick labels on the switch to remind me which position is doing what. And because the patron boxes are slightly sloped, I added some self-adhesive rubber feet to prevent it from wobbling. For a real test I connected my Hacker soldering station, which draws about 70 watts. Initially, when the Hacker boots, the light is off, but when the heating starts, the bulb is on, not on full brightness, just somewhat. I dim the lights to make it a bit more visible. Because of the current limit, the Hacker takes quite a bit longer to reach the set temperature of 350 degrees Celsius, but eventually it gets there. As soon as it does, the heating stops and the current drops by so much that the light goes off, until the Hacker turns the heater back on and the cycle repeats. I find this box a useful tool that can be made very cheaply and fast. I think I spent less than 2 hours building this on a Sunday from parts I got from a quick trip to a DIY store. The longest part was cutting and grinding with a Dremel. If you like my videos, don't forget to subscribe. There are more projects, repairs and reviews coming up, and it would be great if you decided becoming a Patreon. That would really help this channel. Thanks for watching.